So reaction mechanism 19 looks at another hydrolysis reaction, this time ester hydrolysis. So what's interesting about ester hydrolysis is it can occur in both acid catalyzed or base promoted fashions. So I'm going to show mechanisms for both of these. And again, either one would be acceptable considering that you maintain kind of the proper protonation state based on what the environmental pH is. So again, we'll begin with acid catalyzed, which is kind of the more prototypical sort of scenario. Again, having a hydrolysis reaction that's acid catalyzed, we need to think about the species that we can utilize in our mechanism. Remember, water is always a possibility, but in this case, in an acid catalyzed situation, hydronium is the other option. Again, because of that, our mechanism should really only have neutral and cationic species. So if we want to have a leaving group leave, we're going to protonate it beforehand to make it a cationic species, leaving as a neutral species. Again, water not being a great nucleophile, we're going to facilitate its nucleophilic attack by protonating the carbonyl oxygen. That actually is going to be the most basic ester atom of the ester functional group. I'll show you on the next slide why that is. And again, that allows that carbonyl carbon to be more electrophilic, better able to react with the less nucleophilic water molecule. And again, we'll highlight too that this is an acid catalyzed reaction since we regenerate the acid in the final step. That's kind of a hallmark of something that is catalysis, is we speed up a reaction, but we don't consume a species in the reaction. So let's go ahead and sort of highlight what's going on here. I'm first going to draw an ester and highlight for you why we have a certain atom here be more nucleophilic than the other. So again, we've got two oxygen atoms that we have here, which could potentially be protonated. But if we think about potential resonance structures we could draw here, we could move these electrons and bounce them up to that other oxygen atom there. Right, resonance structures, oops, and I drew the wrong arrows there for resonance structures. Resonance structures are going to be more favorable as long as we don't have atoms without complete octets. And again, we're putting charged species on the most appropriate atoms, whether they're more or less electronegative. Again, neutral things are going to be obviously preferred. So this is a minor contributor in terms of a resonance structure. But what that highlights for us is that when we have a resonance hybrid, which really kind of says what's the net sum of potential charge on this oxygen atom up here, it's going to be partially positive. And this oxygen atom has a partial negative charge up here, partial positive charge down here. Again, just highlighting for us that this is the most basic atom that we have here, meaning if we have the potential to protonate something, it's going to be that specific species. So let's then begin with our mechanism here. I'm going to redraw my ester here. We do want to protonate, and we're going to use acid to do this. We're going to have our acid sort of shown here. Protonation makes this guy a better electrophile. So that it's better able to react with our weaker nucleophile, which is water. Nucleophilic attack generates our tetrahedral intermediate. And again, if you had wanted to show this next step happening in concert with the first one, that would not have been inappropriate. Oftentimes we can combine sort of protonation and or deprotonation and chemistry steps together, but we're going to show it separate here. Deprotonation of what was our incoming nucleophile to generate a neutral intermediate here. And actually I'm going to show in this previous step at the same time protonation of this group to make it a better leaving group. So now we've made our alcohol be a good leaving group here. Our water is no longer the best leaving group. So that leaving group, its departure is facilitated by an adjacent heteroatom that can donate its lone pair of electrons to generate a pi bond carbonyl. We have our leaving group leave. And this generates our alcohol. And then our protonated carboxylic acid. Easy to sort of have this be deprotonated here to generate our final product, carboxylic acid and an alcohol. So here's our carboxylic acid, here's our alcohol, and I'm just going to highlight here that we will be left with an acid here. So the fact that we have regenerated this guy so we've regenerated our acid, which confirms the fact that it was a catalyst. So again, that is the mechanism for ester hydrolysis in an acid catalyzed fashion. We're going to look now at what happens if we consider a base promoted catalysis. And I'm going to highlight the difference in the semantics with this nomenclature, that there really is a difference between saying something is acid catalyzed and then in this case base promoted. So again, hydrolysis reactions that are base promoted, we're going to be using hydroxide. And so the only two species that we can utilize in our mechanism are water and hydroxide. It was water and hydronium in our previous mechanism, water and hydroxide here. So similarly, our mechanism is really only going to have neutral and anionic species. So again, leaving groups leaving by being protonated, that's not something that happens under basic conditions. In this case, we're basically going to have it just depart as an anionic species. And because of the environmental conditions we're in, that's okay. So again, now we consider nucleophilic attack here because we have a more basic nucleophile in hydroxide rather than water. We're able to do chemistry more easily with the poor ester electrophile. We don't have to protonate that electrophile to make it more electrophilic. And again, we couldn't do that under these environmental conditions. If we're under basic conditions such that we have hydroxide around to serve in this base promoted fashion, we're not going to be able to protonate our carbonyl. So again, this chemistry is termed base promoted because we're going to have this powerful hydroxide that promotes the chemistry, and catalysis would not be an appropriate terminology since we're not regenerating that hydroxide, so we can't use that terminology. As we're going to see here, this mechanism is actually quite a bit simpler because we don't have to have the protonation and deprotonation steps that we saw in our previous mechanism. So starting now with our ester, which we don't need to protonate and can't protonate under the environmental conditions we're in. We won't also have to worry about deprotonating water because it comes in as its more nucleophilic hydroxide. So nucleophilic attack here. Okay to have this alkoxide anion here because remember, we're going to have intermediates that either are neutral or negative. So here's our intermediate. We're going to take this intermediate and have our leaving group leave. And as we highlighted, it's okay to have that leaving group leave as an anionic species because of the environmental conditions that we're in. The last little piece that we would probably wrap up with here is to consider the fact that these two probably aren't in appropriate protonation states given that we know that the environment is basic. Probably not basic enough to fully deprotonate our alcohol, but certainly basic enough to deprotonate our carboxylic acid here. So deprotonation chemistry. And one thing I'm going to highlight is it would be appropriate to draw this as a one-way arrow because ending up with a carboxylate and then an alcohol is such that this carboxylate is certainly never going to be basic enough to deprotonate the alcohol functional group here. And this alcohol, again, having a pKa of somewhere between 15 and 16. So it didn't really have any biological context to sort of talk about here, but ester hydrolysis is really important when we think about how we take triglycerides, for example, and we're going to cleave that ester linkage to get free fatty acids so that we can utilize transporters in our gut to sort of pull those in from our intestinal tract. Also really important when we think about how we make soap. And again, similar chemistry that we think about with taking triglycerides and snipping off those fatty acids so that we can use those to generate our micelles that we can use for cleaning.